How exactly does time dilation work? That is the question. Consider these two images, which are nearly identical here. Uh, they're both images, right? But what if I were to tell you that one of these images, it was not actually an image at all, but simply a running video of a newlywed couple, where the people in the photo were just standing very still. How would you be able to tell the difference, right? Or how, when you say, for an instance, when you look at an image on your TV screen where nothing, in the video is changing, how would you know that your TV was on pause, or if you were still looking at a running video if nothing was changing, right? Uh, you wouldn't be able to tell the difference. So you sort of see where this is going, right? Time, as it were, is basically just the process or evolution of physical change. You know, this of course makes a big assumption that there is no, say, invisible, like grandmaster clock in the backdrop of the universe that runs, independently of whatever is or is not happening elsewhere in the universe at any given time. So now let's define it this way. Let's say we define times in terms of units of change, aka the transfer of energy from point A to point B. Uh, Consider this a simple case of an enclosed system, which basically is two electrons which are exchanging a photon of energy back and forth like two people playing catch. Forget about minutes, hours. How could we define a unit of change for this simple system? Well, when the photon leaves the electron on the bottom, that electron is going to lose energy, and later the electron on the top gains this energy whenever it receives that photon or absorbs that photon. Then the photon leaves the electron and the energy is returned to the first electron again. The cycle then repeats itself over and over and over. Uh, Now, this simple process basically allows us to define a unit of change. Namely, 1 unit is basically just one cycle of a photon going from the first electron to the second one and then back down to the first electron again. Let's call this unit of change, let's just say it's like 1 photon second. Now, what if we took this simple system here and we suddenly started accelerating it to the right? You know, uh, sorry, my right. Suddenly it's going to take longer, if you do that, it's going to take longer for the photon to complete its cycle because it's going to have to travel some horizontal distance between the electrons, which means the electrons will be losing or gaining energy at a slower rate than they were before. Uh, thus I guess you could say we have slowed down the evolution of change for this system, and by definition, we have slowed down time. Uh, how much slower will the electron lose or gain energy? Well, if the two electron system is traveling at speed v, the slowdown factor can be mathematically calculated to be the what's called the Lorentz factor, just using some simple grade 10 mathematics. It's this right here. And you'll see similar problems like this in your grade 10 math class, where you have problems where it's, instead of a photon going back and forth between two electrons, it's a man in a boat having to cross a river, and there's a stream in the river, that or current in the river, that's going a certain speed, and the question is, all right, how much longer is it going to take if the speed of the boat is c and the speed of the current is v? How much slower will it take him if he's going, in this case, against the current to get straight across from point A to point B before? Well, it would be the same Lorentz factor right here, and you've probably done this yourself at one point when you were in grade 10. Now, anyway, but back to time dilation. Now, one might think that this result cannot be generalized to larger and more complex enclosed systems like our little, you know, ping pong system here with the two electrons and photon. That's not say that's much more simple than say a spaceship full of people. You know, think of that spaceship from the 1968 film Planet of the Apes, for instance, where however, when you, but I'm getting off track here. If you think about it, everything, no matter how complex it is, everything is still made of particles like electrons, atoms, protons, neutrons, and all of these particles interact and change with one another through the transfer and exchange of energy. And energy uh, travels at the speed of light via, you know, via one of the forces. In the case of a photon, it would be the electromagnetic force, of course. But you got your, you got your gravity, your strong force, and your weak force, and all these forces can transfer energy, and they all do it at the same speed, which is the speed of light. Uh, Thus, if we take any system of particles, no matter how complex the system is, it could be a spaceship, no matter how many particles are in it or how they're arranged, uh, and we take this system and we accelerate it to a speed comparable to the speed at which energy transfer exchange occurs, we slow down the evolution of physical change. And as such, all events within this enclosed system, they're going to take longer to occur by our definition. All right, and that's how you get time dilation happening. Things start slowing down. All right, I hope you like this short video. If you want to see more videos about videos of mine about physics and weird stuff like quantum, check out my other video about quantum mechanics. Do we live in a simulation? Quantum weirdness. Can information theory explain the weirdness in quantum? Anyway, it's a fun video. Go check it out. Thank you.